Today we're going to be talking about Snell's law and refraction of light. But before we get into refraction of light, we need to understand reflection of light. So let's say I have an object here, and we're going to call this glass, okay? And I have my ray of light that is going to come in and hit this glass. Typically, when we think of glass, we think of an object that is going to reflect light, or essentially bounce light back off in a different direction. So what we typically see with light and reflection is that the angle at which light comes in compared to the normal force, so I'm going to write force normal, this angle right here, this angle of incidence, is typically equal to the angle at which light is reflected. So we're going to call this the same. So angle of incidence here at this angle is going to be equal to this, and that is reflection. But what happens if we have an object, or sorry, not an object, what happens if we have light and a medium that is different than glass? For example, we have water. So I'm going to write water down here and air up here. Okay. So what happens if we have this normal force again? Here, draw normal force. And we have light that comes down and hits the water. Typically, what is observed is that light will thus bend into the water. Now the question is, why does it bend? And that's what Snell's law refers to. It is basically looking at the angle at which the light enters, which we'll call the angle of incidence, and the angle at which light bends. And we'll call this the angle of refraction. And that looks like a V, so refraction. Okay. So, what we know is that each of these mediums, both air and water, have indexes of refraction. So air's index of refraction, we're going to label that as N, is equal to 1. Whereas water's index of refraction is equal to 1.33. So slightly bigger, but not too much. But the trend that we see is when we have a lower index of refraction going to a higher index of refraction, we end up with a angle of refraction that is actually smaller than the angle of incidence. And we see that the angle of refraction actually bends towards the normal force. So, for example, let's say you have, I'm going to make this red. Let's say you have mud, and you're in a car, and you are driving on the road, and you're coming in at this angle. At a certain point, your tire, your front right tire, is going to hit the mud first. Now, mud is very thick, it's very dense, and so this tire right here is going to decrease in velocity, so it's going to slow down. Whereas the rest of the tires here, here, and here, their velocity is going to be constant. I'm just going to put constant. So, in turn, your vehicle is going to shift and kind of pivot until it all hits the mud. In which case, instead of going this way, your car is now going more this way. Not perpendicular to, or not parallel with the normal force, but more of an angle that is towards the normal force. And this is a trend that we see with light. Light ends up slowing down and ends up bending towards the normal force. So we have the sine, the incidence, sine theta of the incidence, and the sine theta of the angle refracted is equal to the velocity of light in air versus the velocity of light. No, just write a velocity of light in water. Okay. So this is one of the versions of Snell's law that you'll see, where it compares the ratio of the angle of incidence and the angle of refraction as compared to the velocity of the light in the air and the velocity of light in the water. Oops. Okay. So, we know that velocity in this situation is equal to the speed of light, which is 3 times 10 to the 8, over the index of refraction. So we're going to consider this V air, and this in air, and the speed of light is the same for both. So we can then use this to derive the other equation for Snell's law, which is more commonly seen. So if we substitute in, so if we cross multiply here, we get that sine, we get that velocity of water times sine theta incidence is equal to velocity in the air times the sine theta angle of refraction. Okay, so then we can use this equation here to substitute in for the velocity. So we get speed of light times sine theta of the incidence of refraction over the index of refraction in the air. No, apologies. In the water, which would be equal to speed of light times sine theta of refraction over the index of refraction of air. Okay, so now we have that. We can then multiply both sides by NW and NA. Multiply both sides by NW and A. We'll see that we'll cancel out these, and we cancel out these, which would leave us with index of refraction of air times the speed of light, sine theta, index is equal to speed of light times sine theta, angle of refraction. If we divide both by the speed of light, seeing as they're both the same, we then get the index of refraction in the air times sine theta of angle of incidence, which is equal to, which is equal to index of refraction in the water times the sine theta of refraction. So this right here is our second equation. It's important to understand that light does not always travel from a lower index of refraction to a higher one. In the case that we see with air to water. However, sometimes you get the opposite, where you will get an ray of light coming from the higher index of refraction to a lower index of refraction. So let's say we have, again, water on the bottom and we have air on top, but we have the light source coming from the bottom to the top. Two things can happen here. We can have a refraction, and we can also have a reflection. So this is just typically what is observed in light in general. However, we are going to say that this is now our angle of incidence, and that this is now our angle of refraction. So if we go back to the thought process of a car and mud, right? So when light leaves a higher density substance, or a higher index of refraction, to a lower one, typically it's going to refract away from the normal force here. Okay, but we still have the two options. Well, you can either go and refract, or you can completely just internally reflect. And those are two options that we have. So what we're going to do now is look at what happens when your angle of incidence becomes exactly 90 degrees. Because eventually, if you keep increasing this angle right here, this angle of incidence, your refraction is also going to, your angle of refraction is going to also increase. So what I'm saying is, if you increase your angle of incidence, you are going to therefore increase your angle of refraction to the point where it hits 90. So this angle of refraction, bends at 90 degrees. Okay, so let's go ahead and try to calculate this. We have Snell's law here. We have N1, and we're going to call N1, we're going to say that's equal to air. And N2 here, we're going to say that's equal to water, which is 1.33. Okay, so N1 sine theta incidence is equal to, N2 here, I apologize. Yeah, is equal to N1 sine theta reflection. Okay, so we are going to look for the angle of incidence, which once it hits 90 degrees, our angle of incidence is equal to what we like to call our critical angle, or theta C. Okay, so N2 is equal to 1.33, and then we're looking for sine theta. Just put this all in real quick. N1 is equal to 1, and then sine theta reflection, or sine 90. So sine theta of incidence is equal to 1 sine 90 over 1.33. Go ahead and calculate this. The theta of incidence, which is, we said was equal to our critical angle, is equal to 48.75 degrees. Okay. So going back up here, we're saying that this angle right here, this angle, 48.75, is equal to 48.75. Okay. So when our angle of reflection is equal to 90, we then know that our angle of incidence, or what becomes our critical angle, is equal to 48.75 degrees. Go ahead and write degrees. Okay. So what happens if we increase our angle here, and make this greater? So instead of it being equal to, what happens if we make this greater? Well, let's calculate it. We know that our angle of incidence is 48.75 degrees. What happens if we then make this, let's say, we make our angle of incidence 50. Okay, so we'll take N2 sine theta incidence equal to N1 sine theta reflection. We said that earlier N2 was 1.33, so 1.33 sine, we said we were going to make that 50 degrees, and then 1 times sine, which is what we're looking for. So 1.33 sine 50 over 1 is equal to sine of r, theta r, sorry. And if we take the inverse of this, 1.33 sine 50, I'm just going to go ahead and do it on my calculator. You get the inverse angle of 1.012. Oh, whoops, sorry. 19. And if you know anything about trigonometry, you know that you can't have an angle, a sine angle, that is greater than 1. So this actually can't happen. So that's actually not possible. Now, why is that? Because once you reach a point here, once you reach a point where your angle is going to be greater than 90, then you no longer have refraction. You now have what we call, I'm going to write it here, internal reflection. You can have reflection or refraction, but at a certain angle, once you pass 90 degrees of refraction, of the refraction angle, you are therefore now reflecting in.